Hello, welcome to lecture 23. In this lecture, we're going to start by talking about the magnetic force between current carrying wires.
Let's build our concept first. If we have a wire, I'm just going to draw it going straight up and down, and if that wire carries current I, I'll just say that it's moving straight up and the current is I1. What we know is that current carrying wire will have magnetic fields which exist around it in big circles. You can use your right-hand rule to show that the orientation of the circles go in behind the wire and they come out in front of the wire as I've got drawn here. So this is something we've covered already. Any current carrying wire makes a magnetic field around it. The magnetic field around wire 1 is B1 equals mu naught I1 over 2 pi r, where r is the distance where we're trying to find a magnetic field. Let's say that our distance r is the radius of the circle I've drawn here. So now let's ask, what if I pop in a second wire? So I'm going to put in a second wire right here. When the wire is just on its own, it wouldn't feel any force at all. We know FB equals IL cross B. So if there's no current, there's no force. But what if I put in a current on this wire? So let's say that this has current I2, which heads upwards. Well, now to find the magnetic force on wire 2, we'll have I2 times L, the length of the wire, crossed with the magnetic field it's sitting in, and the field it's sitting in is the field made by wire 1. Okay, so there's the idea. Wire 1 makes a magnetic field. Wire 2 carries a current, so it feels a force. We can calculate what that force is going to be, and we'll go on to the next slide to do that. Okay, let's get to doing that a little bit more rigorously. So here in my picture, I've got wire 1. It's carrying current I1, which is going up. We'll draw our magnetic field again. We're trying to find the force on wire 2, so we're drawing our magnetic field so that the field is where wire 2 is. So there's our magnetic field. I get the direction of the field from my right-hand rule. So now let's write down that wire 1 makes B1 at the position of wire 2. We can write down what the magnetic field is. The magnitude is mu naught times I1 over 2 pi times r, where r is the distance between the two wires. Okay, now what about direction? I'm going to say that wires 1 and 2 are in the same plane, so the direction of the magnetic field where wire 2 is into the page. So right here at this point where wire 2 is, the field is into the page. And that's something we've done in previous examples. If you'd prefer to draw a two-dimensional picture, you certainly can. There's wire 1. Here's wire 2. Not the best drawing, but hopefully you get the idea. Distance between them is r, and the direction of B1 at wire 2 is into the page. Okay, so if wire 2 is carrying a current I2, then wire 2 is going to feel a magnetic force because it's sitting in a magnetic field. So wire 2 feels a magnetic force due to B1. We want to find that magnetic force. The magnetic force on wire 2 is equal to the current in wire 2 times the length of wire 2 crossed with the magnetic field it's sitting in, B1. So this is I2 times L times B1. That's the magnitude. We can get the direction using the right-hand rule. So with the right-hand rule, you point your thumb in the direction of the current or the length. Those are in the same direction. So your thumb should be pointing straight up. You extend your index finger so it points in towards the screen. So if you want to picture like playing guns as a kid, you're shooting a little gun in towards the screen. You extend your middle finger and you should see that your middle finger is pointing towards the left. So the direction of the magnetic force is to the left. There's the force on wire 2. And that comes from the right-hand rule. I could say to the left, but I think I'm just going to stay really generic and I'm going to say it points towards wire 1. Because that direction would be true no matter how we rotated our wires. Now I'm going to fill in what I know for my B1. I2 times L. B1 is mu naught I1 over 2 pi r, where r is the distance between the wires. Okay, so this gives us an expression for the force on wire 2 due to wire 1. Let's write down this general expression. So the force, magnetic force, is equal to mu naught times I1 times I2 times 2 pi times r, the distance between the wires. Force, of course, has a direction. We see that wire 2 is pulled towards wire 1 if the current is in the same direction, so the force is attractive when current is in the same direction. And I'll leave you to try for an exercise. You can also see that it's repulsive when current is in the opposite direction. So now you might also ask, what is the force on wire 1? And that would be a really great question to ask. I'd invite you to hit pause and see if you can think about it for a moment before we write it out. So Newton's second law should hopefully come back to you, even though maybe it's been a while. If wire 1 pulls on wire 2 with the force we've written down, then the force on wire 1 is equal and opposite of that force. And that just comes from Newton's third law. Now, of course, you can work through it if you wish. If you draw your two wires, wire 1 and wire 2. I won't put all the detail in it. Wire 2 has current that flows up, so it makes a magnetic field that makes big circles. The direction of those circles come around like this. So the direction of the magnetic field at wire 1 is out of the page. So the strength of B2 is mu naught I2 over 2 pi times r. The magnetic force on 1 then is I1L cross B2. And that would be I1LB2 towards wire 2. And then I kind of ran out of room, but you could fill in for your B2 that it's mu naught times I2 over 2 pi r. You'd see that you get exactly the same expression that we wrote down for wire 2. Let's do an example now. We have two circuits. The one on the left has a 9-volt battery and a 2 ohm resistor. And the one on the right has a 9-volt battery and a resistor with a resistance we don't know. The wires, the vertical parts are 10 centimeters long and the two left and right ends are separated by 5 millimeters. What we're asking is, for what value of the resistor, so that's our resistor R, will the force between the wires be 5.4 times 10 to the minus 5 newtons? So with resistors connected to a battery, that means current is going to flow in each of these circuits. We'll have two current carrying wires close to each other. They're going to experience a magnetic force. So we know that our magnetic force is 5.4 times 10 to the minus 5. Let's try and put all that together. Let's look at our circuit on the left first. So current comes out of our 9-volt battery, goes up and to the right through the 2-ohm resistor. After it passes the resistor, it comes through and goes down. So there's our current that we can call I1. We can definitely calculate our I1 because we know the potential and the resistance. Let's think about the magnetic field that I1 makes. So in the vertical part, the current is flowing down. We know that the magnetic field will make big circles around the wire, and we care about what is the field at the second wire. So there's our big circles where the wire is at the center and the circle cuts through the place where we care about the field. Let's try and get the orientation. Your thumb should be pointing down and you make a circle with your fingers. And you ask, what are your fingers doing over next to the segment on the right? Your fingers should be coming out of the page towards you. So the direction of the field right here is out of the page. And we can label this field B1. In our second circuit, current is coming out of the 9-volt battery, up and through the resistor, and down through the loop. There's our current I2. So a current carrying wire is sitting in a magnetic field. It's going to feel a magnetic force. Let's start to put these things together. Let's start by figuring out what is B1. So B1, the magnitude is mu naught times I1 over 2 pi r. R is equal to 5 millimeters. Let's find our I1 before we go any further. So V equals IR, so I1 equals V1 divided by R1. V1 is 9 volts, R1 is 2 ohms. 9 volts over 2 ohms gives us a current of 4.5 amps. Let's go back to our expression for our magnetic field. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps times our current I1, 5.0 amps. Divide that by 2 pi r. And what we get is 1.84 times 10 to the minus 4 Teslas. That's the strength of the magnetic field at the bit of wire in our right-hand circuit. So the bit of wire with current I2 flowing down is sitting in a magnetic field with a strength of 1.8 times 10 to the minus 4 Teslas. We've already established that the direction of the magnetic field is out of the page. So I'll put in my coordinate system X, Y, Z, and I'll call Z, positive Z, out of the page. Okay, so we know there's current carrying wire sitting in a magnetic field. It's going to feel a magnetic force. Let's write down that equation. The magnetic force on that segment of wire is equal to the current in the wire times the length of the wire, that's 10 centimeters, crossed with the magnetic field that it's sitting in, B1. Okay, why don't we do the vector version here instead of doing the right-hand rule version? So we've got I2. We don't know what I2 is because we don't know R. It's equal to I2. The length of our wire is 10 centimeters. The direction is the same as the direction of current. Current I2 goes down, so the length vector points down. So we've got 0.10 meters, J hat negative. That's crossed with B1, which is 1.8 times 10 to the minus 4 Teslas, K hat. Okay, so we've got I2, that's negative, 1.8 times 10 to the minus 5, multiplying negative 0.1 and 1.8 times 10 to the minus 4 to get a negative 1.8 times 10 to the minus 5. That's Teslas times meters, J cross K. Okay, I'm completely out of space. We'll move over to the next slide. On the next slide, we'll fill in what is J cross K. So you might remember, or you might do your little trick, J cross K is going to give us positive I. So let's write our force now in the vector form. Force is equal to minus I2 times 1.8 times 10 to the minus 5 Teslas meters. J cross K, we already said was I. So there's our force on our segment of wire sitting in the magnetic field. Okay, now we're given that the magnitude of that force is 5.4 times 10 to the minus 5 newtons. So that's going to be equal to the magnitude of minus I2 times 1.8 times 10 to the minus 5 Teslas meters. And the magnitude is just giving us a positive number, I2 times 1.8 times 10 to the minus 5 Tesla meters. Okay, so you can see in our expression now we can solve for I2. I2 is 5.4 times 10 to the minus 5 newtons divided by 1.8 times 10 to the minus 5 Teslas times meters. That gives us an answer of 3 amps. Now we know that the current flowing in the right-hand circuit is equal to 3 amps. We know the potential of the right circuit, so we'll call that V2. And we're trying to find the resistance R2. So let's apply our Ohm's law here. V2 equals I2 R2. So R2, which is labeled R in our picture, is equal to V2 over I2. V2 is 9 volts. I2 we just found was 3 amps. So for our answer, we get 3 ohms. For this example, we have 2 springs attached to a metal bar, and the springs have spring constant 10 newtons per meter. It says that the springs are compressed by 1 centimeter when a current passes through the wire. What is the current? So we're going to find both magnitude and direction for our current. So let's think about what the problem tells us. The springs are compressed. If the springs are compressed, there must be a force that pushes them to the left. That means that there's a magnetic force that points inwards. Okay, if our springs are compressed, we know that a spring pushes back towards equilibrium. It means that our spring on the top pushes our bar out to the right. So there's a spring force. There's also a spring on the bottom that also pushes it back out to the right. Another spring force. Okay, so now we have a free body diagram where the forces we have in our diagram are magnetic and spring force. We're going to neglect gravity. Let's assume that our rod is light enough that the gravitational force is small compared to our spring force and our magnetic force, and that our bar doesn't actually droop very much. Okay, so if we have a free body diagram, we've written down our forces. Why don't we write Newton's second law? Sum of the forces on our bar in the x direction is equal to mass times acceleration in the x direction. So we've got one spring force to the right, we've got another spring force to the right, and a magnetic force to the left. Our bar is not moving left or right, so it's compressed and then it stays still. So the net force is equal to 0. What are we going to put in for each of our forces here? The magnitude of our spring force is going to be the magnitude of the spring constant times the magnitude of the compression. The spring constant is 10 newtons per meter, and the magnitude of the compression is 0.01 meters. So that equals to 0.1 newtons. So that comes from a spring force equals minus kx. The magnitude of the magnetic force is equal to the magnitude of the current times the magnitude of the length times the magnitude of the magnetic field. We don't know the current, let's just leave that as I. The length of our wire is given in the picture, 20 centimeters. And the magnitude of the magnetic field is also given in the picture, 0.5 teslas. So the magnitude of our magnetic force is current times 0.1 teslas times meters. Okay, let's put all this together in our Newton's second law equation. 0.1 newtons plus 0.1 newtons minus I times 0.1 Tesla meters equals 0. Solve for our current I to get 2 amps. Okay, that takes care of the magnitude. What about the direction? Is it flowing up or is it flowing right? Let's use our right hand rule. So we extend our 3 fingers. We know that our thumb is the direction of our current. We don't know what that direction is. Our index finger is our magnetic field. That has to point out of the page towards us. And our force, our magnetic force, is our middle finger. That needs to point to the left. So you need to rotate your arm, your body, your hand, however you can, so that your index finger is pointing straight at your face. Your middle finger is pointing to the left. You should see that you have to point your thumb downwards to get that. That means that the current must be flowing down. So our net current is 2 amps in the downward direction. In this example, we have 2 wires pinned on the ground and they're separated by a distance r. These, let's label in our distance there. Why don't we do some labels as we go? Separated by distance r. These 2 wires carry current I in the same direction. So the current in the first wire is I. Current in the second wire is also I. A third wire with mass M is carefully placed above the midpoint of the 2 wires, so right above the top there. Right, the top of the triangle is right above the midpoint of the bottom, and is seen to hover such that the 3 wires make an equilateral triangle. So this length is R, this length is R. If it's an equilateral triangle, all the angles in the triangle are 60 degrees. Okay, what is the current in the third wire? So if it's hovering, what that's telling us is that the net force on that top wire has got to be 0. So let's write that down. Sum of the forces on that top wire equals 0. Sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. So what forces do we have on that top wire? Well, gravity pulls it downwards. And also, that's a current carrying wire near 2 other current carrying wires, so there's a magnetic force. We know that gravity pulls it down, so the magnetic forces must be holding it up. So let's write down the sum of our forces. The magnetic force due to wire 1 in the y direction plus the magnetic force due to wire 2 in the y direction minus the force due to gravity must be equal to 0. And of course, all x forces will have to be equal to 0 as well, so it doesn't move left or right. So let's see if we can sort out these forces. Wire 1 has a current flowing into the page. Our third wire, wire 3, has a current flowing out of the page. When we talked about the forces between current carrying wires, we said that wires that carry current in opposite directions will repel. That means the force on wire 3 due to wire 1 is straight away from wire 1. So that's the magnetic force on wire 3 due to wire 1. It's a vector, of course, so it does have our x and y components that we talked about. There's the x component, there's the y component, and our angle here is 60 degrees. Okay, so why don't we go ahead and figure out what the y component of that vector is. FB1y, so the magnetic force on wire 3 due to wire 1, the y component, is FB1 times sine of the angle. The magnitude of the force we covered when we talked about the force between current carrying wires is the current on wire 1 times the current on wire 3 times the length divided by 2 pi r, where r is the separation between the wires, times the sine of the angle between them. That angle is 60 degrees. Okay, I'm going to say that my current in wire 1 is I times my current I3 times L times 2 pi r. And last, I'll just fill in that sine of 60 degrees is root 3 over 2. If you wish, you can leave it as sine 60, or you can fill in numbers. Doesn't really matter. Okay, that takes care of the force on wire 3, the top wire, because of wire 2, because of wire 1. What about the force due to wire 2? Okay, so those wires carry currents in opposite directions, so the force is going to be repulsive. So there's the force on wire 3 due to wire 2. That's got an x component and a y component. I'm not going to go through the sum of the x forces. If you wish, you can go through it and you would see that that's equal to 0. So my FB2y is going to be exactly the same as my FB1y. It's because the magnitudes of those forces are the same because the currents in the wire are the same. So because I2 equals I1 equals I. So FB2y is mu naught times I3. I'm going to write a little smaller here so I can squeeze it all in. 2 pi r root 3 over 2. Okay, the last thing we're going to do now is put our magnetic forces in with our gravitational force, and we remember that Fg is just mg. So let's write all that in Newton's second law, and we'll spill over onto the next slide to do that. Let's keep going with our Newton's second law here. Fb1y plus Fb2y minus Fg equals 0. Remember Fb1y and Fb2y, those are exactly the same. So that's the same as doubling Fb1y. So let's fill in what we have. 2 times mu naught times I3 times L over 2 pi r times root 3 over 2 minus mg equals 0. Trying to solve for our I3 here, so let's cancel out those 2's. Mu naught I times I3 times L over pi r times root 3 over 2 equals mg. And we'll solve for our I3. I3 is equal to mg times pi r divided by mu naught times I times L times 2 over root 3. Okay, there's the current in that top wire, which will make that top wire float above the ground.